Hello, I'm Austin Wyndham. Welcome to Teammates Homework 5 Intro to Deep Learning presentation. So our problem, what we're doing here is that we're trying to implement and enhance the diffusion-based generative models to generate realistic images from noise. So diffusion models, state-of-the-art, used for a lot of image generation tasks for their sample stability and sample quality. And the significance is that these models are widely used in computer vision, robotics, and then inserted in Gen AI tasks. Continue on this problem, most of these do in pixel space, which is slow, so we're going to use a VA to implement in latent space, and then we're also going to implement a classifier for guidance to steer generation without a separate classifier. And for our task, we have DDPM from scratch, full diffusion process in pixel space, DDIM to speed that up, and then latent DDPM, which is the VAE, which allows us to do this in latent space, and then classifier for guidance, label conditioning during training and inference. And there are data sets, ImageNet 100, it's around 130K images, a bunch of different classifications, and then results be evaluated with FID and IS metrics. And then going to our approach methods, our pipeline. So we start with the input image. This goes to the encoder, gets us that image in latent space, DDPM, DIM, then is able to generate, works on that. We get the latent output, decodes that, and that gives us our output image. So for DDPM, what happens in diffusion is that you take an image, you add noise over time, it kind of learns that, and it's able to reverse the process, and it goes from noise to then an output image. So this UNet architecture that we use allows us to do that process. And then DDIM, which is alternative to DDPM reverse process, reduces the number of noisy steps, helps to go faster, and that's deterministic sampling, so you can go from the same input to the same output. And then latent diffusion methods, this is implementing the VAE. So instead of operating in pixel space, which is much slower, we can operate with latent vectors, and this just makes the whole process much faster. Classifier for guidance. We're able to train the model with and without labels, and then during inference, combine conditional and unconditional outputs, and this controls strength of label influence with the guidance scale.
So we evaluate our models with two standard measures. The first is Frechet inception distance, or FID for short. It tells us about the overall match between real and generated image distributions, and the lower this score, the better. Usually below 50 shows an excellent performance. And next measurement is inception score. It tells us about the image clarity and variety of classes, and the higher this score is, the better. Above 7 should be good enough. For the results, for the basic DDPM, we got FID score of 326 and inception score of 1.8. Visually, the outputs are still mostly covered noise, but after adding the DDIM scheduler and moving the process into VAE latent space, we see that the textures and shapes started to appear. However, the numerical scores haven't improved much. The reason is simple. We have trained the latent model for far fewer iterations, but it learns much faster, about 6 times faster in general. The key takeaway from this study is that the new pipeline is already giving clear images with the same compute budget, and we expect the FID to fall and inception score to rise once we continue training with this model further and add classifier free guidance. And to summarize, we rebuilt DDPM, added DDIM for quicker sampling, and proved that latent diffusion can learn meaningful structure with limited hardware. And diffusion models still remain computational heavy, but our modular code now lets us test better architectures, longer training, and improved noise schedules for the future work. So these steps should bring the FID below the desired 50 and make the model useful for the real applications. Thank you for your attention.